Hello all together, and now this is just the remainder of our sheet about linear maps. The last one, 3.3, number 5, it was about identity map, just because this is what's written here on the right side. But actually it's about the question, how can you show that such, and also how can you explain why such a combination of matrix applications, matrix multiplications, results in the identity map. And so if you look at this matrix A, you remember our last topic, it was about rotation matrices, and it's quite obvious that these are famous numbers which correspond to the sine and cosine of certain well-known angles. Okay, especially we remember, and now that's the question where to put in. Yes, if you remember that this angle of pi fourth, which is half half a right angle. Sorry, I wanted to say that this one has a sine and cosine, which are both the reciprocal of square root of 2. Why is this? Of course, it's because this corresponds to a I think it's called isosceles triangle. You know what I mean? Isosceles triangle. It's a right triangle with a right angle, but it's also isosceles. So now that's why. Okay. But anyway, look back. Where was it? I think here. This is the general form of a rotation matrix. So if we find the cosine of a certain angle on the diagonal, and the sine, once with a plus sign, once with a negative sign on the second diagonal, then we can identify it as a rotational matrix. And so in this case, it must be the angle of pi fourth, because its cosine is written here, its sine is here, and this is the minus sign, the negative sign of the pi fourth angle. So that is actually a matrix which rotates the whole plane about this angle of pi fourth. So if it's squared, it means it's applied twice. Okay, it's applied and again applied once and again. So that means we have a rotation by this pi fourth angle, then again, which means now meanwhile it's a rotation by a right angle. Then this B matrix obviously performs a, how do you say, point reflection at the origin, or a central inversion. That's what it does. In the end, it's just a minus identity map. So it just replaces any vector by its opposite. So that's why, in the end, if we do this, which means we rotate about a right angle, then we we perform a central inversion, and then again we rotate by a right angle, we have the identity. And this is what I just sketched in this little picture here. You see, imagine just any this point as no, start here. Let's say this is any arbitrary, well, vector, of course, but I just represent with this point in the plane. Okay, you see, and now this is rotated firstly by 90 degrees, then it's central inverted, so point reflection at the origin, and then it's rotated again, and you know, in the result, this means it's transformed into the original vector again, into the pre-image, you could say, right? So right angle rotation, then also such a central inversion is exactly the same as a 180 degree rotation. So a rotation about P, about an angle of P, will result in exactly the same as this central inversion, you know this. And so everything's clear now, but one thing's interesting. How can we use now our matrix theory to prove that a central inversion has exactly the same effect as a rotation by an angle of pi? Can you tell me? If you look here again, the same procedure saying that this is obviously a rotation matrix, which we found out by just guessing that This is the cosine of pi fourth. Could we do something similar here? Any ideas?
Well,
But I just told you that
pi
yeah.
is 0 and cosine of pi -1.
That's it, right? Exactly. And because the cosine of pi is -1 and is written on the diagonal, it fits. And with the sign of yes, right, of pi, which is 0, it doesn't matter plus or minus 0. So that's it, exactly. Fine, great.